in Switzerland. I'm also chair of IEEE Switzerland and a member of a few Region 8 IEEE committees. It is my pleasure, and I'm really happy today to be sharing with you my work devoted to the analysis and modeling of medical electronic devices by using three-dimensional simulations. Okay, so my talk today will be as it follows. So it's actually consisting of two parts. In part number one, I will be presenting you cochlear implants, and in part number two, I shall be presenting you insulin pens. In each presentation, I'll give you a brief introduction of what that device is. Then I'll move into presenting you the modeling for both devices. And then I shall end up by giving you simulations results for both devices. And I shall conclude and give you future perspectives. I want to mention that for the modeling of these medical electronic devices, I have used ANSYS tool with HFSS and Maxwell 3D modules, respectively. Okay, so now the time for part one, cochlear implants. Okay, so as already pointed out, I shall give you a general description of what cochlear implants are, also emphasizing on the design goals. Then I shall focus on the main idea of my project, which is actually the fact that I have identified that climatic changes affect a lot the quality of sound in the cochlear implants. For the first time, I proposed the addition of temperature and humidity sensors to compensate for this. I shall give you an overview of the antennas, both the radio frequency transmitter and receiver, which have been included in a cochlear implant and properly optimized and modeled in 3D. This will be followed by an analysis of a classical loop antenna with precise dimensions. Then I shall give you, lastly, simulations results regarding the radiation pattern, Smith charts, electric field, etc. Okay, so now I shall briefly talk to you about what a cochlear implant is. A cochlear implant is used by people that are suffering severe hearing loss disabilities. So they have either completely lost their hearing, which might be due to a damaged auditory nerve. Therefore, the normal amplification of the sound signal, which is done by a simple hearing aid, no longer works, and therefore a medical surgical procedure should be done to implement or to equip the patient with a cochlear implant. And this is a medical surgical procedure which costs approximately $60,000 US dollars and is done by medical doctors under full anesthesia. But just before jumping into giving you an overview of the cochlear implant, I would just like to mention that there are approximately 360 million people in the world suffering for various degrees of disabling hearing loss. Approximately 330,000 people have cochlear implants. This means that approximately 1 in 1,000 people with some hearing loss would have a cochlear implant on themselves. If you have a look here in figure number 1, you can see that the cochlear implant is basically made up of two antennas, one in the outside and the other one in the inside of the body, which are connected via a radio frequency link, therefore wirelessly. At the outside, close to the ear of the patient, we would have a speech processor equipped with a microphone. This microphone is actually used to pick up the sound signal from the outside and then transmit it to the antenna, and therefore further on to the inside antenna. Lastly, at the very end, it will reach the electrode array in the antenna, the electrode array into the cochlea, in order to make an electrical stimulation of the cochlea. In this way, we are actually bypassing the damaged auditory nerve in order to electrically stimulate the cochlea via an array of electrodes. In order to do so, the sound signal will be transformed into bits by the digital signal processing block of the external unit and sent out via a radio frequency link to the second antenna in the inside of the body, and therefore the now electrical signal will reach the cochlea and stimulates it. In this way, we recreate the initial sound signal from the outside that a normal person would have heard just by having the auditory nerve properly functioning. It is worth noting that some of the design goals of this type of implantation are the insertion depth. We don't want to make it too deep or too shallow. We just want to insert it at the right depth. We want to have the coupling as efficient as possible. And obviously, we want to reduce the insertion trauma, because actually this type of operation consists of actually drilling a hole in your mastoid bone in order to attach the antennas and in order to have the patient equipped with the cochlear implant. Obviously, we have a wireless communication between the two antennas, which is actually reducing possible infections and increases the patient comfort. To extend the battery life of the external unit, it is worth pointing out that we do not have, obviously, a battery in the internal unit. We only have a battery in the external unit. Otherwise, we would need to change rather quickly the implant. So therefore, to extend the battery life of external unit, one must have a low power design of the full ASIC implementation. Okay, moving further into my presentation, I just want to give you two examples of people using or needing cochlear implants. On the left-hand side, you see a child, a baby, a young baby, with a cochlear implant. On the right-hand side of the slide, you can see a sportsman. And here you can see that they might be more affected by the changes in the climatic environment. So this will affect then their ability to recreate the sound. So people having dynamical lifestyle may be exposed more to climatic changes. Therefore, the cochlear implant would be more affected in terms of the electrical signal having a lower quality, being more attenuated. And then, of course, my objective for this project was, as I already stated, to compensate these climatic changes, especially temperature and humidity, which are affecting the sound quality of the cochlear implants, by placing temperature and humidity sensors. It is really worth pointing out that this has not been done before. As you will see, that there are other techniques, I would say, at the moment that are used to compensate the temperature and humidity issues that we are experiencing. Okay, so I just pointed out the fact that any type of environmental concerns affect the quality of the sound. Therefore, any type of rain, wind, transpiration, or snow makes the sound becoming unclear or makes the device shutting down completely. So we obviously don't want to do that. We don't want to be experiencing that issue. What we did actually was really nice and interesting. I was fortunate to be part of the Entrepreneurial Project here at the Swiss Federal Institute of Technology in Switzerland, to be able to deploy my idea for this project and to be able to talk to the shareholders and to interested companies that are developing themselves either hearing aids or cochlear implants. I wanted to say that my project was selected as a class project, and the idea was recognized by main players in sound quality, such as Phonak or Sonova. So I had the chance to interview more than 30 people, approximately half female and male interviewees. And I was able to see by asking them the right questions, I was able to see what their inconveniences are related to wearing hearing aids or obviously cochlear implants. So some of them were wearing hearing aids, some of them were having some cochlear implants on themselves. Obviously here, if you have a look at this pie chart, on the left-hand side down, you can see that humidity accounts for 42% of their inconveniences. So it really makes sense to address the humidity issues in cochlear implants. On the right-hand side, on the downside, you can see the age of the people that we've interviewed, and you can see they were quite young in age. Okay, I was mentioning you before that there are nowadays some techniques to address the humidity, which are quite, let's say, ancient, if I may use this word. So what they would normally do with the hearing aid, for example, or with their cochlear implants, they will place it in absorbent chambers, or they will immerse it in hydrophobic capsules, or directly place it under an electric dehumidifier, as we normally do with the air in our house. So for them, removing the implant and placing it directly into a dehumidifier. Okay, this is really cumbersome. Is not really pleasant for the patient. So this comes in the idea of really making a cochlear implant being able to compensate for humidity in a different way by producing or proposing, first proposing and then producing, yes, the fully equipped electronic solution to account for this compensation of both the humidity and temperature issues. Here, if you want to learn more about the main constituting blocks of the cochlear implant, you can have a look at this schematic that we have prepared for you. So basically you have an external and an internal unit, which are separated by skin and bone, and you have a radio frequency link in between them. Obviously, as I mentioned before, the signal which comes from the outside of the body should be converted into bits to be able to be sent over via the RF link. So this is the job of the DSP unit. In the internal unit, as there is no battery, it is the job of the stimulator to firstly derive power from the radio frequency signal. Once the stimulator is charged, it can then decode the RF bit information, and it then can convert it into electric currents for the electrodes. It is really worth pointing out that we have a back telemetry feedback loop, which really accounts for sending back processed signal back into the external unit. And this really accounts for the critical electrical and biomedical signals within the implant. And it's really tasked with sending it back to the external unit. Okay, we were also focused on producing a multi-layer physical model. It means that we were really able to look into the equations governing the propagation of the signal, which is obviously a wave. The sound signal is a wave, electrical wave. And then we were able to characterize via mathematical equations how the signal is being affected while being transmitted from the outside of the body, from the initial transmitter antenna to the receiver antenna on the other end, which is already placed inside the skull of the patient, closely located to the mastoid bone. So we don't get into the brain. Therefore, we would have two main physiological tissues to take into account, skin and bone. You can have a look at figure number 3 and figure number 4, which are giving you, firstly, in figure 3, the ideal waves propagation from lossless to lossy medium. And then we have prepared the anatomical multi-layer model with 2 to 3 layers. 2 are sufficient to get a valid model. In table number 1, one could see the main parameters of the tissues that we have in the human body, which are concerned with the implantation. Okay, if you want to look more, let's say, or deeper into the physics of this multi-layer or bilayer tissue model, one can look obviously at the time average power flow, which is given by the Poynting vector, as you probably remember from the courses in physics. This is given by the real part of two important electric and magnetic intensity vectors strength. And then, of course, you can have a look here at the bottom. You can have the equation governing this attenuation. So we have various attenuation constants of both skin and bone. And then one could get the exact equation for the electric field strength. Okay, further on, we had proceeded to doing the three-dimensional model of the antenna. So we have been looking into both the antenna in air. Here you can see it in the left-hand side. And we have also focused on addressing the antenna placed in a bilayer tissue model, both skin and bone. Therefore, the second case is valid for the antenna, which is placed inside, whereas the first model could refer to the antenna placed outside of the body, the external transmitter antenna, which is actually placed, obviously, just in air. We have looked into exact, precise dimensions of the antenna. So you can here have a look. You can have a look at their exact dimensions. So it's approximately 3.5 by 3.5 by 0.03. If you say in millimeters squared, or if you go in centimeters squared, and then once again you multiply by the depth and you get to the power 3. So you have cubic dimensions here. Obviously, it is worth pointing out that we had looked into the proper data transmission frequency, which is approximately 2.45 gigahertz. You are probably familiar with this frequency because this is part of the ISM band, which is used for medical applications. Okay, so we have done some electromagnetic simulations in ANSYS HFSS. Okay. So, when we are talking about antennas, we are really much interested into looking into the Smith charts, scattering parameters, etc. These are very useful for radio frequency designers, as they show the reflection coefficients, the scattering coefficients, different admittances, impedances, noises, etc. Here you can see the relationship between T, uppercase T, chain scattering or chain transfer parameter, and S, scattering parameter. And then here we have then proceeded to doing a frequency sweep between 1 to 3 gigahertz. And for the antenna placed in air, we have here different Smith charts. And on these Smith charts, you have the scattering or the S parameters. Obviously, it is a symmetrical system, so S11 equal to S22, whereas S12 equals to S21. Here, if you want to have a look, you have the same results. By now, we have taken into account the antenna placed in skin and bone. So we are now referring to the inside antenna, which is the receiver antenna. We were also interested to have a look, obviously, at the electric field. And we were very much interested into looking how the electric field for the designed loop antenna changes from purely air to then a multi-tissue model on the right. And therefore, you can see that obviously once the sound wave, once the signal is starting to circulate or to be transmitted from the outside to the inside, it encounters various media, it encounters various tissues, and is therefore attenuated to a certain extent. One could see here how much is being attenuated, quite a lot. So via our simulations, we found out that there was a decrease of 87% in the electrical field, which is normal. And then we reached a maximum value of 0.73 volt for the antenna placed in multi-tissue model, whereas for the maximum electric field in the antenna placed in air, we had approximately 5.6 volt. Once again, I mentioned that all these simulations have been done in ANSYS HFSS by employing a frequency of 2.45 gigahertz. You can see here on this slide, you can see the 3D polar representation of the total radiated electric field. This is showing up in figure 13, which is on the left-hand side. And then on the right-hand side, you can see the total radiated electric rectangular contour plot. Obviously here, we were interested to look as well into the radiated electric field because there is radiation, obviously, of the wave. And then you can see here all the numerical values. What it should really be pointed out is the fact that while you are looking at the hot zones, you have to look for the red. So this is a color-coded map for figure number 13 as well as for figure number 14. So color-coded map is showing us the hottest spots. And here we could reach a maximum of 0.73 volt for the radiated electric field. In figure number 14, you have the rectangular contour plot of the total radiated being taken from 180 degrees to minus 180 degrees to 180 degrees. And then for the theta angle, you just only have positive from 0 to 180 degrees. Okay, so here, if you are interested, you can have a look at the loop antenna placed in air, and we have produced here the return loss. Because, of course, it wouldn't be a discussion on antennas if we didn't look into the return loss. While we looked into this, we could see that the resonance frequency was around 2.7 gigahertz. One could ask now, but why was it not resonating at 2.45 gigahertz? I would say that this was the first attempt to do the antenna, and then we had to center it by manipulating different parameters in our simulations. But this was really the first trial to see where it resonates, and then we had to finally tune it to be able to resonate at the frequency that we really wanted to. So to center this minimum point here of the resonance frequency to where we needed to have it. Okay, so we were also interested to look into the total field versus theta angle, and some radiation patterns are always a must to look into. So one could have a look at this slide and see information about these important parameters. And obviously, if you are interested to learn more, I'll give you at the very end some publications that I've published. One you can look to what you need to learn more about. Okay, so now I shall conclude the first part of my talk, which was really focused on presenting cochlear implants. and the 3D physical simulations to evaluate and assess the performance and to optimize these types of antennas in cochlear implants. So we had the antennas with the careful chosen dimensions, which are dimensions which suit the patient. So these are the dimensions that are being currently employed for this type of cochlear implants. We have characterized the antennas, both the outside and inside one. We have given Smith charts for the antennas and the scattering coefficients for antennas placed both in air and by tissue layer model. As future directions, I would just like to mention that the next step would have been to fabricate the antenna physically, or let's say electronically, and to be able to test it. But I just want to point out that this was only a 6-month research project that I received the funding for. I was principal investigator. It was my own grant. And after these 6 months, you can imagine that in this time, there is really not much time to do circuit integration. And this was also beyond the scope of the project itself, which was mostly to optimize it from a physical point of view, from a 3D point of view, and then to subsequently integrate it if we had the chance. You never know, maybe in the future. Okay, here, if you are interested to learn more, as I pointed out, you'll have a few references of my publications. I would really welcome you to read more on those. Okay, so I really wish to thank Hassler Foundation from Switzerland for providing me the grant to do this research. Okay, so now moving into part number 2, I would just like to say that part 2, I'll spend the time on insulin pens, and then if there are any questions, you can address them at the end from both parts. So obviously, if in the meantime any question is coming up to your mind or you want to have it answered, please also don't hesitate to write it in the chat. That will be most welcome. Okay, so part number 2 is devoted to insulin pens. At the very beginning, I mentioned to you that I'll be talking about medical electronic devices. One can ask now the question, but is the insulin pen really an electronic device? Okay, it is a medical device, but is it really an electronic device? And one could say, no. One could argue, no, it's purely mechanical. Why are you mentioning that it's an electronic device? You'll see about that. You'll see about this. You'll have the answer to this question very, very quickly into my presentation, a little bit further on. Okay, so giving you a summary of this second part, I shall be presenting you a 3-dimensional physical model for the capacitive measurement in an insulin pen used by diabetic persons. Again, this was issued by a company. So we had a company that had a patent on this, and they came up to us to develop the electronics of an optimized insulin pen for diabetic persons. I have used ANSYS Maxwell 3D software to faithfully model an insulin pen and to subsequently numerically assess the electrode capacitance, which is very much needed in the dose evaluation. You'll see there is a direct link between the dose and the capacitance. We have tried to look into multi-electrode configurations, 3, 4, 6, and 8. And we have also looked into various dimensions for the thickness and length of these electrodes. We have computed the capacitances values for these electrodes in various biasing conditions. So this is just in general. You'll see more specifically later on into the presentations what we have been tasked to do. But just I'll spend a few words on, of course, again, mentioning what diabetes is and what type of methods are being used to address this issue. Approximately 463 million people being affected by diabetes. Is actually it was in 2016 the 6th most deadly disease in the world. So that's quite a lot of deaths being attributed to diabetes. It can be of type 1 when the pancreas does not produce enough